Welcome to lecture number 22 of this statistical thermodynamics for engineers. So previously, in the previous section, we found out that, when you analyze the vibrational mode of energy, we can use something called a harmonic oscillator, okay, which is close to the actual Morse potential. And the Morse potential, if you recall, is given by these two fitting parameters. Out of that, this parameter dE is particularly important because it designates the dissociation potential. So the harmonic oscillator works very well when the distance r is within a particular band of the equilibrium internuclear radii, internuclear distance. And when r goes to infinity, you have the dissociation. So normally, when your potential is less than dE, we have a stable bond between the two nuclei concerned. So let us now analyze the vibrational mode. So this is given as d square dx square plus 2 mu h square bar e vibrational minus half k naught into x square into s equal to 0, where s is r, capital R, okay, and x is r minus re. Okay, this is all assuming harmonic oscillator. Okay, so you assume harmonic oscillator, and therefore this is the expression that we write. So this is basically your star, and this is basically your x. Okay, all right. So now put hy equal to sy to exponential y square by 2. For y is equal to 2 pi mu gamma divided by h bar half into x, right? And lambda equal to 2e vibrational divided by h mu. Okay, so if we put all these things now in this expression, so you have now, we proposed three things. We have proposed that h is equal to sy into exponential. We have put y equal to 2 pi mu frequency divided by h bar into x. And then we have put lambda is equal to this, right? So that's like a wavelength. So lambda is equal to this. So as you can see over here now, putting all these things together, putting all these, okay, you have d square h by dy square minus 2y dh by dy plus lambda minus 1 into h is equal to 0. Okay, so this is the expression, this is the reduced form of the expression after we applied all the variable changes. So this solution is given by the Hermite polynomials, right? Hermite polynomials of degree, let's assume v. Okay, so the solution to this particular equation is again an ODE, second order. So get h e minus 1 v exponential y square dy dv divided by y v exponential minus y square. Okay, for continuity, which continuity requires v equal to half lambda minus 1, v equal to 0, 1, 2, da da da. Okay, so this is called the Hermite polynomials, okay, of degree v. Hermite polynomials of degree v. Okay, so the complete solution, complete solution is SV lambda half into x 1 over, okay, 2v factorial into half alpha by pi raised to the power of 1/4 exponential alpha x squared by 2 multiplied by the Hermite polynomial alpha half x, where alpha is given as 2 pi nu gamma divided by h bar. Okay, so this is the total expression that you get. Okay, and this is the expression for your alpha. Expression for your alpha, where alpha is 2 pi nu frequency divided by h bar. Okay. So you get the point now. So now your lambda is 2 vibrational level divided by h nu. Okay. So v equal to half lambda minus 1, okay, which leads to the fact that lambda minus 1 is equal to 2v, or lambda equal to 2v plus 1. Okay, so therefore 2v plus 1 is equal to 2 vibrational divided by h nu. Okay, or E vibrational is equal to v plus half h nu, v equal to 0, 1, 2, da, 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 da. Okay, so for v equal to 0, okay, v equal to 0, that is for the lowest vibrational energy level, energy level, 0 point energy, is E vibrational equal to half h nu. Okay, so for the harmonic oscillator, E vibrational is equal to E square by 2 nu plus E naught x square by 2. Now, if E vibrational was equal to 0, say for example, means both E and X have to be equal to 0. have to be equal to 0, okay. That, if that was true, then this will invalidate Heisenberg uncertainty principle, Berg certainty principle. Got it? So so that's why the vibrational energy cannot be equal to 0, right? So the 0-point energy, if you look at it, so the lowest vibrational level is always half h nu. Okay? Got it? So if now go to the next page, if wave number, wave number space GV, let's put it as GV, vibrational divided by HC, that is equal to V plus half into omega E, V equal to, once again, 0, 1, 2, da, da, da. Omega E is equal to gamma by C, which is nothing but the frequency. I mean, from the frequency, K naught is like the spring constant, equal to that. So this is in the wave number space. So vibrational quantum number, okay, uniquely determines the Hermite polynomial, the Hermite, okay, polynomial, or in other words, the G vibration is equal to 1. That essentially means that the degeneracy is 1. So vibrational degeneracy is equal to 1. Okay, there's only one type of way that you can have a vibrational mode. Okay, so if you look at now a few of these vibrational solutions, the solutions of SV, okay, alpha half into x. If you look at some of the solutions, like for example S naught will be alpha by pi 1/4 exponential minus alpha x squared by 2. S1, which is alpha by 4 pi 1/4, that is equal to 2 alpha by half into x exponential minus alpha x squared by 2. Okay, S2 is equal to alpha by 4 pi into 1/4, then 2 alpha x squared minus 1 exponential minus alpha x squared by 2. Okay, and S3 is equal to alpha by 4 pi 1/4 into 2 alpha p by 2 x cube minus 3 alpha half into x exponential minus alpha x squared by 2. All right, so these are the few solutions of this of the vibrational, first few solutions for the harmonic oscillator model that we have. Okay. So now let's look at the kind of a roadmap. Okay, so rotational and vibrational energies of diatomic molecule is modeled as bands. Okay, you can have this bands now. Okay, so it is called, this is the rigid rotor, okay, which translates to fixed internuclear distance. Nuclear distance is RE. And on the other side, you have the harmonic oscillator. Which basically it mandates, what is this mandate? Mandates small vibration around RE. Remember, small vibrations, not large. Okay, so this fits nicely into that. Okay, so around RE, this is RE, this is the well, right? So this is RE, so it just vibrates around this particular level within a particular band. Okay, so what it implies is that small RE, for small RE, okay, ensures that that Morse potential is well approximated by the harmonic oscillator. Okay, and that is in general, that is ties very well with the rigid rotor model, because R is fixed, invariant, and therefore there is only a small amount of oscillations about R, and that is what ensures that this is oscillation is kind of well behaved, so to say. Okay, so that brings us, so we will do one more small example thing. Okay? Say for a one-dimensional, the steady state. Okay, Schrödinger wave equation. Okay, for one-dimensional, harmonic oscillator in Cartesian. Cartesian is given as 1 degree of freedom, one-dimensional, chi divided by x square, 2 mu h bar e vibrational minus half a naught x square I is equal to 0. Okay, so hence the wave function is basically sigma v, okay, describing the one-dimensional harmonic oscillator. It describes a one-dimensional harmonic oscillator. Equivalent to SV. All right. Yeah. Okay, so you can, we want you to show that chi naught and chi 1 are orthonormal. Okay. Okay, all right. Okay, so first and foremost, proper normalization requires minus infinity to plus infinity. I star chi d chi. Sorry. x is equal to 1. Okay, so if you just look at these numbers that we just pulled out, these numbers, okay, you just look at those numbers over here. Okay, what you have for v equal to 0, v equal to 0, okay, the integral will be I naught square dx is equal to alpha divided by pi into half. Writing the integral below, plus infinity exponential of minus alpha x square dx. Okay, so this translates to, if we do the integration by pi half, pi by alpha half, this is equal to 1. Similarly, for v equal to 1, that is a second wave function, that is minus infinity to plus infinity, psi 1 square dx equal to 4 alpha, alpha by 4 pi, okay, raised to the power of. Again, we are writing the integral in the next line, minus infinity to plus infinity, x square exponential minus x square into dx. Okay, this is equal to 2 alpha, alpha by pi half, pi half, 2 alpha 3 by 2 is equal to 1. Okay, so the two wave functions are properly normalized. Okay, so now, so they are these two wave functions. Two wave functions, they are therefore properly normalized. Properly normalized. That's good. So now we recall that if two wave functions are orthogonal, two wave functions are orthogonal if they are orthogonal, right? So if you take the product, the two in this case, that means from minus infinity to plus infinity, it should be 0 psi 1 into dx should be equal to 0. Okay, so what we can do is therefore we multiply the two wave functions now. So therefore we evaluate plus minus psi naught into psi 1 dx, which is equal to now alpha 2 by pi raised to the power of half. Again, I'm writing the integral in the next line, plus minus infinity exponential x into exponential minus alpha x square into dx, okay, is therefore equal to 0. This you can validate. Okay, this integrand is clearly an odd function of x. So the integrand is clearly an odd function. Okay, so this kind of shows that, you know, this is how you analyze. So we have seen that how the vibrational energy and the rotational energy and the translational energy can be done. Now we can extend this kind of an analysis for the electronic energy mode of atomic hydrogen, electronic energy mode of atomic hydrogen. You can extend it. So atomic hydrogen, okay, you know that you have now this rigid rotor, harmonic oscillator, the degeneracies, you know the energy levels, you know basically everything, right? Now atomic hydrogen is composed of what? One proton and you have one electron. Okay, so it is almost like the two-body analysis. It's like, you know, the two-body analysis that we did. Right? The two-body analysis that we did. Therefore, we can again separate the external and the internal energy by transforming to a center of mass and relative coordinate system. Except here, the only viable electronic internal mode arises from the electronic structure of the atomic hydrogen. So here also we can do the same thing. We can separate the external and internal energy modes. Okay, you can separate the internal and the external energy modes by transforming to a center of mass type of a system and relative coordinate system. Except you should just note here that one thing that happens, okay, that the only viable internal mode, okay, arises from the electronic structure. Of atomic hydrogen. Okay, of hydrogen atom. Okay, so in the next class, what we are going to see, we're going to use the same separation of variables and kind of try to justify that how this thing can be attained. Okay, how this thing can be analyzed further. Okay, using our knowledge that we gained from the previous analysis. Thank you.